Now this last week for me has been really busy. I've been working, well, up and down the country, so I haven't been at home very much. So when I got home late on Friday night, I found I had this huge bag of goodies that we're going to have a look at today. Now before we get started, we better just clear some space. Now at first sight, all these purchases are going to appear a little bit random, but there is some method to my madness which hopefully will gradually reveal itself. Or then again, it may just be madness, so yeah, bear that in mind as well. So let's move that, keep that. Oh, I don't know what's in there. Take that. Well, I think this is going to be one of the most interesting packages, so let's get started with this. Now, I think that this package has come all the way from China, but I've got to admit I'm not totally sure. If I can find the details inside the package, I will let you know. Actually, I've just noticed it does have a UK address on it. Greenford, wherever that is, but I suspect that this equipment still does originate in China. I think I bought these off eBay, and we have 3 of them, and they're all the same. Oh, and I'm getting that lovely, aroma of, you know, oily preservatives. I love that smell. I'm putting the others on the floor because they're all the same. Okay. Ooh, a little empty box. I think something's fallen out. Let's tip everything out. Well, that certainly looks quite overkill for what I've got in mind, but no matter. So what we've got here is a ball screw. So for those that watched my CNC video the other week, you will see that the table and the cross slide on that CNC machine, basically it used a long screw thread to basically push or pull the mechanism across, you know, to pull. It used a screw thread to move the table, and also to cross travel the cutter, and also to move the cutter up and down. So everything was powered by effectively screw threads, and then at the end of the screw threads there was a stepper motor. So what we've got here today is a ball screw. Now I actually did purposely choose quite a large ball screw, and yeah, I'm kind of thinking perhaps I actually ordered something, you know, a little bit bigger than I needed, but yeah, this is what I've gone for, this is what I've got. So let's have a look inside these packages. Now this is a bearing of some description, and there's a couple of these. I think one goes on each end of the shaft, but they are slightly different depending on which way around they go. So just inside here we've got a roller bearing, and that may or may not fit on that end. It does fit, it's a tight fit, which it should be. I've got a feeling this should go on this end though. Which it does. It's a reassuringly tight fit. And for those playing along at home, it is a 20mm, yeah it is, I think I'm pretty sure it's a 20mm ball screw. We've got a specification here. Is it 20mm or is it 12mm? I think it's a 12mm. Sorry, I think I misled you there. I think this is alright, okay. This is a one-piece anti-backlash ball screw. It's a 1605, it's 600mm long, and it's got a 10mm coupler, which is this. So this coupler, this is a flexible coupling, and it's designed to basically, it goes on the end of the shaft here, and this connects onto the end of a stepper motor. But looking at this, I think my eyes were perhaps bigger than my belly when I bought these. I think this would probably be quite a powerful ball screw. I mean, in terms of the thrust it can provide and the torque, but it's also quite heavy. As I say, I don't want to give it away quite yet what I'm buying some of this for. It will probably be a bit of a reveal later. Okay, so here's the other end of that. And again, what we've got here is we've got a rather substantial, well, it looks as though they've got a pair of bearings in there, but basically a rather substantial bearing with, it looks like some form of rubber seal as well to keep any smooth out of the bearings, so that's very nice. Okay, so that obviously goes on there, and it is a very tight fit. There we go. And I think somewhere, although again I can't see it, there should be, well, there it is. Okay, we've got a lock nut which would obviously go on the end of here to keep everything together. So basically the way that this works is you will put a stepper motor on the end of here which will turn the shaft, and if we hold this steady and turn the shaft, you can see that this part will move up and down. I turn it one way and this is the nut section and it goes that way. If I turn the screw the other way, you can see it's moving down. So it's basically just a screw thread. Now what's the difference? Some of you might have never heard of a ball screw. Well, the idea of a ball screw is, well, the conventional way of doing it would just be to have a screw thread, wouldn't it? So we could have a piece of threaded bar with a nut on it. But again, we talked about this in my last video. If you just have a length of screw thread and you put a nut on it, you will find that the nut will rattle about on the screw thread and it has backlash. So basically, if you just used a normal shaft, if you turned it, if you was to turn the shaft for a normal piece of threaded bar, threaded rod, sorry, what you would find is you could turn the screw forwards and backwards there, left and right. You would turn it clockwise and anti-clockwise, and you could probably turn it for a few degrees, but the actual nut wouldn't move, and that's because there has to be clearance between the screw thread on the male part and the female part of the nut. There has to be clearance. If there was no clearance, then you wouldn't be able to turn the screw thread, it would just bind solid in the nut. So there's clearance. Now if you're just making fasteners, if you're trying to, you know, I don't know, bolt a part onto your car, it doesn't matter. But if you're trying to use a CNC machine, you think you tell your stepper motor to move by a few degrees. Now what you actually want is you want that movement, that rotary movement, you want that to be turned into a linear motion forwards and backwards. But if you've got backlash in the nut and the screw thread, which you conventionally would have, some of that rotational motion is lost. And basically what it means is you think you've just advanced your cutter by 0.5 millimetre or so, and you haven't. All you've actually done is you've advanced the screw thread by 1/8 of a turn, and you've just taken up the backlash. But your cutting tool won't have moved. So in CNC machines, in good CNC machines, what they actually have is ball screws. So if you were to actually open this up, you would actually find it's packed with ball bearings, and those ball bearings actually push into the grooves on the thread here, and they effectively grip it tightly. But because they're ball bearings, they can still roll along the screw thread. So the upshot of all that is that you have no backlash in a ball screw. Well, I think I was making a bit of a dog's dinner of explaining that. So basically I've been out to the garage and I've found this length of threaded bar, which at some point in the past I must have welded a nut on the end of it to kind of make it into a bolt. And this is one of the hold down bolts that I use when I'm fixing things down to the bed of my milling machine. So it's just it's a bit of metric threaded bar, nothing more exciting than that. And you can see that I've just put a nut on this threaded bar, and it wobbles. It's not actually a perfect fit. This is quite a coarse thread, and as I said, we have to have some clearance between the female thread cut within the nut and the male thread. We have to have clearance. If there was no clearance, the two surfaces of metal, the nut and the shaft, or the nut and the screw, sorry, they wouldn't be able to slide over each other. They would be effectively frozen, because you need some clearance for this movement to occur. But the problem with that clearance, it leads to this wobble. So all that movement that you're seeing there, well, probably not all of it, some of it's down to the test setup, but a lot of this movement here is just down to the backlash. Well, I'm just going to try and rock this nut forwards and backwards on the ball screw, and you can probably see that there is a little bit of movement, but there's actually practically no movement compared with what we were seeing before with a conventional nut. And even that movement that we're seeing isn't actually the nut. It's not the backlash we're seeing. What we're actually seeing is is my workbench flexing. So I can probably demonstrate that just by pressing down on the bench. You can see my test setup is moving. So yeah, so we're not even touching the nut at the moment and we're getting deflection. So we're actually getting more deflection of my bench here than we are of backlash in the nut. So what that means for us is that any angular motion, whenever we rotate this screw, that angular motion gets converted into linear motion. Well, having waffled on about very little for the last half hour, let's open the next box. So what we've got here is a box of NEMA 23 stepper motors. The holding torque is 1.26 Newton meters. The rated current for these is 2.8 amps. The phase resistance is 0.9 ohms. Voltage current phase 2.5 volts. Not sure what that is. And they've got a phase induction of a phase inductance of 2.5 millihenries. It's showing us the windings here. So these are these stepper motors. Let's get one out of the box. So these stepper motors have got 4 leads coming out of them, he said. Let's double check that. One, 2, 3, 4. So just looking at the connection diagrams here, we've got 2 windings. We've got a set of windings on black and green. So let's just pair them off, black and green. And we've got another set of windings on red and blue. So I'm just going to put a knot in this black and green to remind me that that's them 2 windings. Just a loose knot, and we'll put another knot in the red and the blue. Now it's probably not a very good idea to put knots in wires like this, because it does restrict the flow of the electrons. So you know, when you tie it, don't tie it too tight, or you'll find that no power will be able to get down the wire. So we've got 2 windings, green and black, and blue and red. Now I saw a little trick on YouTube the other day when I was browsing and looking at stepper motors, and it said another way. There's a couple of ways it says you can identify the windings. It said that basically if you get hold of the stepper motor and spin it, it will spin easily. But to identify the pairs, if you find the two wires that are connected to one of the windings, if you short them out and then try to turn it, you'll feel a difference in the resistance. So let's just try that. So yeah, I'm getting a feel for how easy that is to move. Let's just short these together. So I'm actually going to short out the green and the black pair. Oh yeah, and it's markedly different. I can hardly move that. And just to do like a double bind test, let's actually short out 2 of these windings that aren't related. So we're going to connect the green wire to the red. So again, this should be easy to turn now because we haven't shorted out a pair of wires. Oops, that's come off. Have another go at that. Oh yeah, that moves easy again. Let's go back. Let's try shorting out the blue and the red this time. Oh, that one feels even stiffer than before. I wonder what happens if we short all the windings out. I bet I can hardly move it then. I can't move it. Is that amazing? So that's just the magnetism. I guess you get a back EMF which magnetizes the coils, which actually resists the turning force. Yeah, that's clever, that. The other way it said you could identify these windings was just to put an LED across them and see if it glows. So let's try that. So I think you should be able to see that. That's flashing away, isn't it? So if we put it on a pair of windings which isn't a pair, which again, let's just try the black and the red. When we turn it this time, we shouldn't get anything. So there's the black. So this time we shouldn't get anything when we turn it. And there's nothing happening. So this is the stepper motor that I've actually bought to drive this ball screw. And we've got this little flexible coupling, which is basically two pieces of aluminium, and then there's some elasto material, there's some rubbery material between them. I have to admit, it doesn't feel very rubbery, it feels pretty hard. Now hopefully this coupling will fit on one end of our shaft, which I think it will. Oh, there we go. And in theory this end will go on onto our stepper motor, which it does. So what should happen is that the stepper motor will spin this shaft, which will turn our ball screw, which will move the nut up or down, left or right, depending which way you're looking at it. Right, so why am I messing around with ball screws? That was probably what you're asking yourself, and if you're not asking yourself that, you should be. Well, two reasons. Well, the first reason is because stepper motors and ball screws I think are really cool. So that's the most important reason. The second reason is that I got really drunk. Yeah. And yeah, well, what can you say? I got really drunk and eBay. In my drunken stupor, I did actually have a little bit of a plan. But now I've got the equipment in front of me. You know that expression, your eyes being bigger than your belly? I think that this actual ball screw and probably the stepper motor is an order of magnitude bigger than we actually needed for the job. But I guess the thing is now, we've got them now, they're paid for. It's going to cost me money to ship them back. Probably a smaller ball screw, a less smaller diameter ball screw would probably be about half the price. But when I've factored in all the hassle of shipping them back, even if the supplier will accept them, I think we'll just plough on regardless. And yeah, this is what we've got, so this is what we're going to use. So the reason I bought 3 ball screws and 3 stepper motors is because I want to have a go at building my own Delta printer. And look now and you're going to see a clip of what a Delta printer looks like. And you're back in the room. So basically what we need is we need 3 motion drives which will move those arms on that Delta printer and make the hot end actually move over the bed of a 3D printer and actually draw out the you know, the part that we want to make. Now, as you saw on that video, what they had was a belt which actually moved the carriage up and down. Now that's the conventional way of doing it and probably the sensible way of doing it. The reason that they use a belt is probably for 2 main reasons. One of them is because belts move very quickly, so you can achieve high print speeds, which is you know, advantageous because you want to be able to print as quickly as possible. The other reason that people use belts is because, and I think probably one of the main reasons, is that they are so cheap. Obviously a belt cost, I don't know, it probably costs a couple of pounds, doesn't it? Maybe less than that. Whereas this ball screw was 50 or 60 pounds, I can't exactly remember. And I bought 3 of these ball screws. And so you're actually looking at, probably with all the bearings and the other parts, you're looking at a couple of £100 just in ball screws, as opposed to a 50p belt. There's other disadvantage to using ball screws. Now, one of the main disadvantages of using a ball screws is, relatively speaking, compared with belts, is that they're slow. Now, in slow, I mean, they can actually move at quite a, you know, a high speed, but you have a lot of mass here. If you think at how much a belt weighs, it probably weighs a few grams, whereas if I just pull this motor off, I don't know what that is. It's probably more than a kilogram. It's quite heavy, that. Yeah, but it is more than a kilogram. So if we want to make this nut scoot up and down there at a rapid speed. We've got to accelerate a mass. Now, this screw has a lot of mass in it, so it's difficult to accelerate it quickly, which means you end up having a huge stepper motor on the end of it to actually try to make it accelerate, because you need if you want this to accelerate at a certain rate, the quicker you want it to accelerate, and by accelerate you mean you need to make this nut, say, move from this position all the way to this one. You want it to do that. You don't want to wait a minute for it to crawl along. You want it to move from there to there in a second. So you're going to be using a very powerful motor to achieve that level of acceleration, which also means you're using a lot of power, and you've also got more friction. Not a lot of friction for a ball screw, but you have got friction, and if you're doing a lot of repetitive movements in one area, you're going to get a high degree of wear in one area on the screw thread, which again I'm not too concerned about because it's a ball screw and it's not a production environment. But what I'm basically saying for you, probably to use a ball screw for a Delta printer is stupid. It's the wrong way to do it. But yeah, I am stupid. I want to use a ball screw, it's my printer, and this is what I'm going to use. So I'm hoping some of you are going to come along on the journey. It may be a total failure, it may not work. I think that's half the fun.
Well, the king said I was daft to build a castle on a swamp, but I built it all the same, just to show 'em. It sank into the swamps.